Hello, everyone. My name is Xijin Zhang. I came from Case Western Reserve University. Today, I will talk about fungi-mediated self-healing for durable concrete. The motivation of this project is to promote the sustainability of concrete structure. As we all know, concrete easily produces cracks on their surface, and cracking allows faster penetration of water and gas containing harmful substance into concrete matrix. And all of this leads to the corrosion of steel bar and the failure of concrete structure. Therefore, numerous labors are needed for the inspection and maintenance. And traditional fillers containing volatile organic compounds results in environmental problems. In order to achieve the self-healing of concrete, we use this fungi. And all of us are familiar with fungi, like the mushroom we can eat. And their structures can be divided in two parts. Above ground is their fruiting body. What we need is the underground part. We can see some thin fibers here, and when the thin fibers interact with each other and form a large network, it is mycelium. And the fungi strain used in this study is the Fusarium oxysporum. They are no biohazard fungi strain. They have very fast growth rate, and the fungi fibers produced by this fungi, they have very great mechanical properties. And the mineralization processes is the most important part to achieve the self-healing of concrete. So based on the literature review, I compared the mineralization processes by the bacteria and by fungi here. And for the bacteria, some of them, they can produce the ureas, which is the enzyme can catalyze the hydrolysis of urea into carbonate ions. And the carbonate ions can combine with the calcium ions and produce precipitation. However, in fungi, they are well known to produce several types of acid. The most important one is the oxalic acid. And this acid can also react with calcium ions and produce precipitation. And this precipitation can fill the concrete cracks and heal the crack. In order to investigate the feasibility of fungi-mediated self-healing technique, first we investigate the interaction between fungi and the Moda. Here we prepare 4 contrast groups. The PDB is the nutrition to support fungi growth, and M is the Moda, and the F is the fungi we inoculate here. As the last group, as an example, we put the plain Moda at the bottom of the Petri dish, and then put the nutrition medium, the PDB, at the top of the Moda, and then inoculate fungi at the center of the Petri dish. And the mixture design of the plain Moda we show here. In these 4 groups, the first group and the third group we use as the control groups. And only the second group and the last group, we inoculate fungi here. So next, we will investigate their fungi growth behavior in these 2 groups, and to investigate the introduction of Moda influence on the fungi growth behavior. We can see in each group, we have 3 samples here. So we have 6 samples in total in these 2 groups. So based on their growth behavior, we divided this 6 samples into another 3 different groups as ABC. For group A, we include all the PDB F123 sample. And for group B, we contain the PDB MF2. For group C, we contain the PDB MF1 and 3. Based on their growth behavior, we can see when the fungi growing on the pure nutrition, they can get germination at first day and then grow fast. They can cover the whole surface of Petri dish after 72 hours. However, with the influence of Moda at the bottom, in group B, we didn't see the germination at the first day. And we can see the faster growth rate, faster growth between the 72 hours to 96 hours. And then they cover the whole surface of Petri dish after 96 hours. However, in the group C, we didn't see the obvious fungal mycelium development in this group. Based on this, we got the overall growth rate, group A larger than group B, larger than group C. Until now, we can raise one question: why in group B and group C, all these include the Moda at the bottom, but they show different growth behavior here. And next, we monitor the pH in the nutrition medium, and we can see that for the pH in the group A, they located at the lowest level, and then group B, and the highest level, the pH with the highest level occurred in group C. So the pH show the inverse relationship here. Group A lower than group B, lower than group C. So we make some assumption here. Fungi can survive on the surface of Moda, and the introduction of Moda delays the fungi growth. And some of you may disagree with the first assumption here because we didn't see the obvious fungi growth in the group C. And then next, I will show the evidence of the survival of fungi in the group C. Firstly, we measure the mass change during the incubation time. And then here shows 3 groups. We use the PDB group as a baseline because only the physical evaporation occurred in this group. And we can get the average evaporation rate is 0.65 gram per day. And for the PDB F group and the PDB MF2, both of them, we can observe the mycelium development in these samples, and their mass loss trends are similar here. So we divided their growth process into 3 stages, including the germination, mycelium development, and the steady stage. And next, we compare the mass change in the PDB MF group. In this group, we can contain 2 situations here. For the number 2, we can observe the mycelium development. For the number 1, number 3, we can't see obvious mycelium development here. And through the mass change trend in these 3 samples, we can observe that for the peak of daily mass loss in the number 2, they occurred at the 96 hours. And in this stage, we all know the mass change caused by the mycelium development. Similarity, we can find a peak of daily mass loss at 192 hours in the other 2 samples. And we can observe the mycelium development at the edge of Petri dish, which is another evidence of their growth. And the proof 2 is the microstructure of group A, B, and C. In group A and group B, we can see the mycelium development here, and under SEM test, we also can see the microfiber and the spores in the samples here and here. However, in group C, we can't see the clearly for the fungi hyphae and spores. However, with higher amplification factors, we can see the spores grow around the hyphae. Next, we investigate the feasibility of fungi-mediated self-healing. The first one is the evidence of precipitation produced by the fungi when they interact with the Moda. And we conduct the EDS test on the fungi mycelium collect from PDB F1, PDB MF2. Both of them contain the obvious fungi mycelium development. And as a result, we can see without Moda at the bottom, we can't see the calcium ions, calcium ratio here. And with the Moda at the bottom, we can see the calcium ratio here. And for the mycelium come from the lower layer, we can see a higher concentration of the calcium. This is because the lower layer of fungi mycelium, they have closer relationship with the plain Moda surface. They can closely interact with the Moda, and the Moda is one of the calcium source for the precipitation. And then FTIR results confirmed this, the existence of calcite precipitation and calcium oxalate precipitation in the fungi mycelium fiber with the grown with the Moda. Next, we investigate the surface property of the fungi mycelium film. We get the fungi mycelium film from the group B and group A, and the contact angle of the fungi mycelium film from the sample with Moda shows the higher contact angle here as the 134.92 degree. And when they grow with pure nutrition, we got an contact angle of 131.47 degree. So that means when we cultivate the fungi, when they interact with the Moda, we can get higher contact angles. When we cover the surface of concrete with mycelium with stronger water repellency, we can potentially reduce the water infiltration into concrete. And next, we calculate the healing time when we use the fungi mycelium, fungi-mediated self-healing agent in the concrete. Here, first we investigate the growth rate of fungi growth. We use at the beginning of the steady time as the neutral time here, and get a relationship between the surface growth and the incubation time, and get the relationship here. And then we assume we inoculate fungi spores in the concrete structure and to heal the crack with a width of 150 micrometer. And then we calculate the healing time at different pH level based on their different growth behavior. And then compared with bacteria induced healing technique here, they can potentially reduce the healing time at different pH level. Next, we calculate the infiltration rate of the fungi-mediated self-healing concrete and compared it with the regular concrete. For the regular concrete, the contact angle is 40 degrees. And for the fungi-mediated self-healing concrete, when they killed by the fungi mycelium, we can get a larger contact angle here. So they can reduce the infiltration rate to the 70.22% of the regular concrete structure. And this is some ongoing research. We try to explore some strategies to improve fungal growth in concrete. This is the microcapsule contain fungal spores inside, and we introduce them into the Moda. And in the future, we will investigate the self-healing efficiency here. So now we can draw some conclusions here. For the fungi used in this study, they was able to grow on the surface of Moda and produce precipitation. High pH in the concrete will delay fungal germination time and increase the mutual time of mycelium development. Compared with the bacteria-based self-healing technique, fungi can potentially increase the healing efficiency. The water repellency of mycelium would reduce the water infiltration rate, and the microcapsules contain the fungal spores will be investigated as a potential strategy to enhance their growth in concrete structure. Oh, thank you.
Thank you, Xijin. I haven't seen any questions yet in the chat box. So could you go back to the conclusion slide? So of course, the highly alkaline environment inside the concrete is always a challenge for either microbes or fungi, I guess. How do we know like they will actually be effective over time, especially when the concrete is going through wet dry cycling and the pH could be as high as say 13.5 or 13.8. I guess your intended solution is to have capsules to protect them, right?
Yeah.
Okay. And also the fungi, maybe I didn't quite get it. What's the size of the fibrous substance?
For the single fiber used here, about 1 micrometer.
Okay. So are they porous? Are they hollow?
Hollow, yeah, hollow structure.
So in that case, do you think the hollow structure will be beneficial? I mean, having some sort of side benefits like to improve durability of free soil, for instance, I mean, resistance to free soil or to alkali silica reactivity, because they provide additional space to buffer the tensile stress potentially.
Yeah, that's a good point. For the hollow structure, sometimes it's a benefit. In or another project, we observe the hollow structure is beneficial for the absorption of some silicon salts inside of the structure. And they can be part of the, when they build the fungi structure and improve the property of the fungi fiber structure it owns. And in the future, we may investigate how this hollow structure influence the reaction inside of the concrete structure.
Right, because we did some work, I guess one of my collaborators will present today with microcapsules, the same thing, once the capsules release the healant, what's left behind is empty capsules, and they seem to basically serve as solid entrained air. So in other words, you no longer need an entraining agent because these things are basically your entrained air. It's kind of interesting. Okay, I see a comment in the chat box, intriguing and fascinating. Does this apply a wide range of fungi or Musselium or only a specific strain? That's the first question. There are two more questions.
Yeah, this is a good question. For generally the fungi like the subacid environment. So this is the fungi strain we screened from different types of fungi strain and which are able to grow with the high pH.
Okay, the second question, has there been any research done for any changes in bond strength with rebar?
Oh, because this is the we only investigate the self-healing, fungi-mediated self-healing technique in the plain model, not related to the ring burn now.
Okay. How does the heat of hydration affect the mycelium? I guess probably when it implies like when you're dealing with large volume concrete, the heat of hydration cannot be easily dissipated. Probably that would affect the productivity or maybe even survival of these fungi, right?
Yeah, I think so. The heat of hydration and the hydrated product of in the concrete structure maybe influence and maybe delay the fungi growth or kill the fungi spores. That's why we investigate the new technology or new strategies to promote their growth when they interact with concrete.
Right, but thinking along the same line, maybe you know, a solution with nutrients and the fungi could be used for rehabilitation, right? Like if a concrete is cracked and liquid goes in and try to heal it.
Yeah.
Now, when it's directed and mixed in fresh mixture, I mean concrete mixture, how would this affect the rheological behavior or setting behavior? Have you tested? Like workability or?
For now, we didn't investigate the specific workability when we introduce the fungi spores or microcapsules into the Moda to see the influence. Previous study only focused on the mycelium grow on the top, and now ongoing research we try to introduce the microcapsule into the Moda, and in the future we plan to investigate the ratio of the microcapsules used in the concrete, and which is the optimal ratio used here for their workability and property.